Well, I think we can start. So everyone, please welcome Jeffrey Richter.
Well, this is kind of an unusual setup, isn't it? I haven't done this sort of thing before. So hopefully it'll go well for everybody and we can still be some degree of interactivity and keep it good. Let me give you a little bit of background. I recently joined Microsoft almost 2 years ago now, and as we're talking to a lot of customers about, at Microsoft Azure, we realize that a lot of customers don't really understand a lot of the features and everything that's involved in creating or architecting distributed cloud applications. And after getting that feedback so regularly, I decided to go and build this course content on how to architect these distributed cloud applications, and I did it in a technology-agnostic way. So in other words, this is not Azure specific or it's not Amazon specific or any other. It's really just a lot of core concepts about the right way to go about architecting distributed cloud apps. And actually, you're really the first people to see these slides. So there's a couple slides in here, like 2 or 3, that I presented to other people, but all the other slides are brand new. So I'm really testing it out on you to see how well it goes, and then I'm hoping to record this into a multi-hour thing and make it available for the world. So I'm hoping that you'll give me some feedback on this, maybe over the Slack channel. And I can incorporate that in before I record it for other people. So I've been excited because I've been working on this for many, many months, and now I'm finally getting the opportunity to deliver it and see how it goes. I do have a lot of content here, and I had a struggle to shrink it down to fit it into our 2 40-minute slots plus 10 minutes of questions. So I don't have a good sense of timing. As I said, I've never taught all this before, so it's my first time. All right, so without any further ado, I'll get started. So this session is about architecting distributed cloud applications, and it's just about a lot of concepts and things to consider. There we go. So I'll be presenting it to you, of course. I'm Jeffrey Richter, just a little bit about me. Right? I'm a Microsoft Azure software architect now. I'm also the co-founder of a company called Wintellect. We do training and consulting services. We've been in business for maybe, 17 or 18 years now. But most people, if you're familiar with me at all, you're familiar because I've authored a bunch of books in the past. About 18 books in total. But the 3 most recent books I put up here on the slide. The CLR via C#, and the Windows via C++ are probably the most popular of those up there. And at the bottom of the slide, I have my email address and my LinkedIn, if any of you want to befriend me on LinkedIn, and my Twitter account down below. And actually, if any of you have any feedback or questions about this content, I would love to hear from you. So contact me at any of those places, because I'm still working on this, and I would like to polish it up before I record it and put it out there in the public. I assume you can download these slides. I uploaded them yesterday, so I see you're taking pictures, but you have the slides available to you. Okay, so let's get started. Why cloud applications in the first place? Why is this even compelling? So at the top of the slide, I have a graph here that talks about what we used to do in the past, or you might even say present, or I guess past is better, because the other column says present. See, that's the polish I need to work on. So in the past, we used to build services, and the client audience was really for the enterprise or the intranet. In other words, the scale was typically pretty low. But today, we're building services that are for the public at large and for everybody across the internet. So we tend to be building services that need to be able to handle a lot more clients than we had in the past, and those services need to scale. So because in the past we were building things for the enterprise or the internet, the demand for it was relatively stable. You had however many employees at the company, and they were accessing these services, and it was usually a pretty stable number of people. But when you start bringing services over to internet scale, then the scale can be dynamic. You might have 100 customers today, 1,000 customers tomorrow, 1 million customers the next day. And so you need to design your software or architect it so it can scale from handling a very small number of people to very large numbers of people. Then in the past, our data centers were typically a single tenant data center. That is, you would set up the data center for your company or enterprise. But today, because data centers are so expensive, we tend to build them large, and then we run a lot of different things inside that data center, making it a multi-tenant data center. And this is certainly true of the public cloud providers like Amazon and Microsoft Azure. The operations of the past was all done by people, which tended to be very expensive, but today we're trying to automate a lot of that operations management, and by automating it, it makes it a lot cheaper or inexpensive. Scale, we would scale up with a few reliable, expensive PCs. That is, when we wanted to handle more load, we would swap out the cheap PC and we would put in a bigger PC that had more RAM and more CPUs in it and a larger hard disk. But that's not the model of the cloud. The model of the cloud is that instead of scaling up your hardware, you scale out instead, and you buy lots of cheap commodity PCs, and you just run your software on more of those same PCs. And then in the past, we considered failure to be very unlikely. But of course, failure is always possible. A hard disk can fail, a power supply can go out, a network controller can go bad, a router can go bad, and so on. But a lot of times we didn't take this into consideration as software developers, and we just assumed that everything was going to run all the time. But in this new world where we have lots of cheap commodity PCs, failure is much more likely. And we're in a multi-tenant world as well. Again, failure is more likely. And so this means as software developers, we have to embrace the failure now. And we have to do the best that we can with that. Let's see, I got a message. Is it? Okay, I see. Somebody's already befriending me on LinkedIn, is what that is. I'm just making sure the networking is working okay with the Skype call. Okay, good. And then machine loss. Well, because we never considered failure to be such a possibility, a machine going down was catastrophic, and it meant that the service just plain stopped. But in this new world, where we can add more machines at will if we're running in a public data center, and we're designing for failure, then machine loss is really a normal thing and is not generally considered a big deal because something will come along and replace that other machine. So this is kind of setting the stage for why we, as software developers, we do things differently and we architect our cloud applications differently than things that we have done in the past. So, as I say at the bottom, we must do things differently when building cost-effective, failure-resistant solutions. And here I just give two examples, but there's many examples that I'll be talking about as I continue through the slide deck. So one example that comes up frequently is exception handling. In the past, people would catch all exceptions and would stop their service from crashing. And that's because if the service went down, then you couldn't handle any more client requests. So a lot of times people would catch every exception, swallow it, and just keep that service up and running. But really, that's a bad design, because exceptions, unhandled exceptions, means that there's some bug in your program, and some state may very well be corrupted. So if you allow your application to continue running with corrupted state, then the results of the service are unpredictable. So the proper thing to do when you get an unhandled exception is for your application to crash. That deletes all the state, and then to have the application restart running. So in this new world, we would not catch all exceptions. We would allow an unhandled exception to crash the process, and then our orchestrator, which I'll talk more about shortly, will go and automatically restart our service with fresh, brand new state so that everything is running properly. Another really big example, and you'll see I'm going to stress this example multiple times throughout the slide deck, because as I meet with customers and talk to them, this is a very hard one for them to get right. A lot of times we have built communication mechanisms in the past so that when we communicate from one service to another, that communication, the messages were being sent in order, and we could count on the messages being sent exactly once. But in this world of embracing failure, messages are going to be sent out of order because we're going to have multiple machines now all communicating. And also, clients must retry operations. And because they are retrying operations, servers might get the same request twice. Imagine, if you will, that a client sends a message to a server, and then the server's processing that message, but the client gets a timeout, so because it's taking too long. Well, what's very likely to happen is the client will retry and send the message to the server. So it was already processing the message once, but now it has to process the message twice because it received it twice. And therefore, the server must implement the message processing to be idempotent. So this is a really important thing. I'll stress it multiple times. When you are building communication stacks in this distributed cloud app world, your communications must do retries, and your servers must handle the communication idempotently, meaning there's no ill effect if it processes the same message multiple times. And this is a mandatory thing you have to do, and it's really one of the things that makes building cloud applications more difficult than in the past. But it gives you a lot of the benefits of scale and running on cheap PCs and building services that are cost effective and failure resistant. And as I said, I'll talk more about it as I go through the deck. So as I keep saying, cloud computing is all about embracing failure. And there are many reasons why you might be talking from one service to another service, and that service goes down. It may fail for some reason, hardware failure, or it may just stop running for some reason. And here I list some of the common reasons why that happens. Well, the first is it could be a developer-related issue. For example, there's an unhandled exception, which I've already talked about some, where maybe there's just a bug in the program, an exception occurs, it's unhandled, and the program crashes. So that means the service would eventually restart, or a client request might retry and might be redirected by a load balancer to a different client. A different server. For DevOps reasons, the person who's managing the service, they might decide to scale the number of service instances down. In other words, we might have 10 service instances running, and the DevOps person decides, I don't want to be paying for 10 of them, I only want to be paying for 5 of them. Well, in that case, your orchestrator is going to kill 5 of them. Which 5? It chooses pretty much randomly. But what if those 5 are in the middle of processing client requests? Well, there are things you can do to try to go down gracefully, but if you don't do those special things, then you'll just be killed. Those 5 instances will be killed, and those clients won't get a reply. Then they will retry, and when they retry, the request should hopefully go to one of the remaining 5 instances, and then one of those will go and pick up the request and process it. So from the client's perspective, because of the retries, everything looks like it's working fine. Your DevOps person might be updating a service code to a new version. It could be that running inside a bunch of machines is version 1 of some code, and those may be processing client requests. And then the DevOps person decides to upgrade those machines to version 2. Well, that usually means that some of those services that are running V1 will go down, and new instances running V2 will come up. Well, the ones that go down might be processing client requests. So again, the client might have to retry in order to get to a different server so it can go and handle that request that's coming in. The orchestrator that you're using, this is the thing that maps your code onto machines. It might decide for whatever reason to bring some machine down and to move your service to another machine. A lot of them do this for load balancing, for example. They see that the machine is very hot. There's a lot of CPU use, a lot of memory usage on it. But they see some other machine that's not very hot. So the orchestrator might say, well, to cool this machine down a little bit, I'm going to delete the service here, and I'm going to bring it up over here instead in order to load balance the machines better. And that can happen at any time with or without notice to you. So again, you have to write your code to prepare for that. Of course, then there's force majeure, which really means acts of nature that you have no control over. So hardware can always fail at any time. A power supply can go bad. A fan can go bad, which could cause overheating. A hard disk can go bad. A network controller, a router, a bad network cable, etc. I mean, all these things are possible and out of your control. And then there's just data center outages as well. A natural disaster, flooding, power failure somewhere, a meteorite goes and hits part of the earth. It could be terrorist attacks is another reason why that might happen. So since failure is inevitable and is unavoidable, you must embrace it. And you would design your applications in order to handle it. So architect assuming your code, assuming that failures will happen. And operate your services using infrastructure that avoids single points of failure. So examples of that are run multiple instances of the service. If you have data that you're storing, replicate that data multiple times. Use multiple network routers, multiple load balancers, right? Don't have a single point of failure. All right, so let's talk a little bit about orchestrators. And a big part of this, my presentation, by the way, is introducing a lot of terminology and concepts and explaining what these terms and concepts do for you. So one of these terms I'm introducing now is this term of an orchestrator. And you end up using an orchestrator when you use something like an infrastructure as a service platform, offering, or a platform as a service offering, or a container as a service offering, or functions as a service offering. Right? Any of those things something as a service, these are all examples of orchestrators that are available. And the purpose of an orchestrator is to manage life cycle of your application, your service, to manage life cycle, health, monitoring, scaling, and upgrading for your PCs or virtual machines, that's your hardware, and your networking infrastructure, and your code as well. So let me give an example. At the bottom of the slide in the large rectangle is some data center region. So this is some data center public cloud, let's say, that you have decided that you would like to upload your code to, and you want it to go and orchestrate the running of your code. So in every region, there's some kind of service code repository. Now you, sitting at your desk on the globe somewhere, you've gone and written a bunch of code. We'll call this your service code. And now you're going to take that code and you're going to go and upload it into that region's service code repository. So now this code, let's say it's version 1, is sitting inside this region. Now you're going to go back to this public cloud provider and you're going to say, I would like to now start running this code. And you're going to tell it how many virtual machines that you want. So now it's going to start spinning up some PCs or virtual machines. Some cloud providers let you use PCs, so you can run your code directly on the hardware or on the metal. But most cloud providers do not allow that. Most cloud providers will create virtual machines running on these PCs, and then they will put your code into a virtual machine. This makes it more cheap for them to go and run the cloud, right? Because they can put lots of different people services on a single PC by doing this. It's cheaper for them. So in this case, I've spun up 4, let's say, virtual machines, and the orchestrator has taken your code from the repository and has copied it to these 4 machines. Now, the orchestrator is also responsible for networking. So around this, it will usually create a virtual network around these virtual machines or PCs that allows your code running on these different machines to find each other and do communication between each other. So your services can talk to one another. And then usually the orchestrator will also provide a load balancer in front, so that now client requests coming in from the internet can be sent to the data center. They come into the load balancer, and the load balancer can direct those incoming network requests to any of these 4 virtual machines, so that any one of your processes running your service code can handle those requests. Now, another big part of an orchestrator is handling failure. So let's say that on one of these nodes, your code gets an unhandled exception and crashes. You like my animations? I work really hard on these things. Okay, so on this node here, the service code has gone away because it has crashed. Well, the orchestrator should detect that automatically and the orchestrator would go and rerun your service, bringing it back up, and it would be communicating with the load balancer during this time as well. So when your service goes down, it should be telling the load balancer not to direct traffic to that node. And then when the service comes back up, it should be communicating with the load balancer again, telling it that it can now start directing traffic to that node. So that was a software failure that the orchestrator handled, but the orchestrator can also handle hardware failures. So let's say that another node just vanishes off the network. Maybe it lost power, maybe the network controller went down. Again, the orchestrator should go and figure that out and should go and talk to the load balancer to tell the load balancer, don't send traffic over here anymore because the node is offline. So now the load balancer will send the traffic just to any of these three nodes. But the orchestrator is also responsible for fixing this problem. And it will do that by finding some other node in the data center, bringing that node up, putting the service code, your service code, on that node, and then once again notifying the load balancer that traffic can now be directed. Right? So this is one of the great things about a public cloud offering, is that they all provide these kinds of orchestrators that do a lot for you in terms of handling failures. In addition, they do things like scale up. So we can be running these 4 nodes now, but maybe they're pretty busy with traffic, let's say during the day, and so we would like to add a 5th node to our cluster here. So a DevOps person can go to the orchestrator and say, let's go and add another node. And when that happens, the orchestrator will go and add another node to the virtual network, will copy the service code from the repository onto the node, and then notify the load balancer that the new node has showed up. So now the load balancer can send traffic to any of these 5 nodes that are part of the cluster. Right, so this is what we get from Orchestrator, and there's lots of different kinds, like Kubernetes is an orchestrator, Docker Swarm is an orchestrator. I worked on Azure Service Fabric, that's also an orchestrator, and all of them do this kind of functionality, have that built into them. All right, so now let's talk a little bit about getting a little bit more into the code aspect of this, and what is a microservice. So I think the term microservice is an overhyped word. It's really about taking what we used to write as a single application and breaking it down into components. And if you were around in the 1980s like I was, that's also what object-oriented programming was. I used to do C programming for many years of my life. And then object-oriented programming was introduced with C++. And one of the tenets of that was to take this very complex piece of code and then to break it down into these classes or objects. And that gave you more composability. It gave you more code reuse. And software developers found that these abstractions were really useful and allowed them to be much more productive when writing code. Well, this concept of microservices is really just taking that same concept to a different level. Instead of having one program that has all these classes in it, you've now split it up into different programs that can run on different machines. And we call that, we say we're breaking the service down into microservices by doing that. So what I show on this slide here is an example of an e-commerce application that's running in some data center. And here we have our internet again talking to our load balancer. And then here I don't show the virtual machines, but all of this would be running on virtual machines. But I have a service, like the website service, and let's say I want 3 instances of this running. So those would be placed on 3 virtual machines as part of this virtual network that's this cluster inside the data center. And then I might have an inventory service that's part of my e-commerce application. And maybe for this, I only need 2 instances of the inventory service running. And it goes and has a backing data store. So the website service is a stateless service, but the inventory service is a stateful service because it has some kind of backing store here for the data. And that could be something like SQL Azure, or it could be Azure Storage, or there's a million different storage technologies out there that you could use. I also show a third microservice here called the order service, and for this one I have 4 instances of running. So these would be on 4 different virtual machines, 2 different virtual machines for the inventory service, and 3 virtual machines for the website service, all sharing the same virtual network and communicating with each other. And the order service, it may have its own data store as well for any of the data that it needs. I do have a little note here in italics, which is an important tenet of microservices, which is that each service solves a domain-specific problem. And any service that has its own data store, like the 2 on the right, inventory and orders, they have exclusive access to their own data store. That is, it would be a mistake for the code in the inventory service to reach into the orders data store, and it would be a mistake for the code in the order service to reach into the inventory data service. And again, to draw a relationship to object-oriented programming, this is the same thing as data encapsulation, where you create a class, and inside your class you have a bunch of fields, and you make those fields private. That gives you data encapsulation. It's the same thing here. It's as if this data store are your fields, and you want to encapsulate it and not expose those fields publicly to the other services. So only the code in only the code in the order service can go and access the data store data. I'll mention this briefly now. It's nice to create these services like in this way, just like it's nice to create object-oriented classes. But there are some downsides to it too. In fact, there's many downsides to microservices, some of which I'll be talking about as I go through the deck. But one which I'll mention right now is, when you split your data like this, it's very hard, in fact near impossible, to do a distributed transaction. So you might, for example, want to say, well, since this person placed an order, I want to take some items out of my inventory. And I would like to do that with an ACID transaction semantic. Well, because the data stores may be completely different data stores, one might be a SQL database and the other one might be some NoSQL database. Different data stores are walled gardens, and they don't support distributed transactions typically. And so it becomes impossible to do an ACID transaction across different services, which means that you end up doing more of an eventual consistency model as opposed to a strong consistency model. And again, that's another hardship for developers. Developers are used to doing strong consistency with relational SQL databases, and they're not as much used to doing eventual consistency models. But it becomes more likely to be mandatory when you design your services like this. Now, I've been spending a lot of time thinking about microservices and working with customers who have come to me and said, well, we have this monolith that we've had for a decade now, and we've decided that we're going to jump on the microservices bandwagon, and we're going to split our monolith into a lot of services. And then the next question that always comes up is, how do we split that up? Do we split it up so every class is effectively its own service? Do we just say we're going to split it up into 2 services? Like, how do you go about thinking about how to go and split it up? So I have identified 4 reasons, and these are the only 4 reasons I can think of, for why you might consider splitting a monolith into microservices. The first reason, and I think this is the most important, is because you want different pieces of code to scale independently of one another. And really what this is about, it's about balancing cost with speed. Because you might have one piece of code that you don't need to have a lot of instances running, and it's resource heavy. So instead of having that on a lot of machines, you might have it on a few machines, and that saves you money because normally these machines you're paying for on an hourly basis. So the example I give here on the slide, imagine you have some kind of photo sharing internet service where people can go and upload photos that they've taken onto a web server somewhere, and then other people can go look at those photos. Well, when people upload photos, they upload them in full resolution, but we need to go and create thumbnail images of those photos. The code that makes thumbnail images is actually very resource intensive. It has to load the whole image into memory, then it has to run an algorithm on it, which is computationally intensive, and then it has to write the smaller image back out to disk. And if a lot of people are uploading photos, then we need a lot of instances of the thumbnail service, and so we can go and scale it up. So now I have 3 instances running. But let's say now, let's say that was the holiday season. During the holiday season, a lot of times people take photos and they upload them. Then let's say that the holiday season is over, and now family members are looking at the photos, but they're uploading fewer photos to the service. Well, that means we don't need to have all of these running anymore. So we can go and scale that down. Here I took one away from the slide, right? And that allows us to balance our costs of running the service so we can run the service more efficiently. So here we would split our monolith up into these 2 different microservices for the purposes of running these different pieces of code that have different resource requirements with different amounts of scale. And that allows us to control costs more efficiently. The second reason why we might want to split something up, a monolith, into microservices, is because we want to use different technology stacks. Maybe we want to write the photo share service in one technology stack like Node.js, and maybe we want to write the thumbnail service in a different technology stack like .NET. So if we have code that we want to run in different technology stacks, then that's a really good candidate for saying, okay, I'll split one into one microservice, and I'll split the other one into a different microservice, and then of course you can scale them independently as well. But that's the second reason you want to use different technology stacks. The third reason is the reuse example, which I also gave with object-oriented programming. By creating these classes, you get to reuse the code. Well, similarly here, we could have this thumbnail service, and it could be used by the photo share service, and it could also be used by a video sharing service as well. So now we have 2 consumers of this one service, if you will. So that's another reason why you might want to go and split things up. And one advantage of this is that you get to version things independently. So here I'm saying that this is the thumbnail service version 1. And let's say the photo share service is talking to version 1, and the video share service is also talking to version 1 of this. But the team that owns the thumbnail service, they can actually bring that service down and replace it with version 2. As long as the backward compatibility is maintained, and this is mandatory, right? You must be very strict about your versioning and make sure that backward compatibility is maintained. So now the thumbnail service can introduce new features over here with V2, as long as it still supports the V1 contracts. And then in the future, the photo share service can, at its own time frame, as I say, clients can adopt the new features at will. This can go and update to version 2, or this can go to version 2, and they can do that independently of each other, right? We don't force everything to version all at the same exact time. So that's the third reason. And now my fourth and last reason is kind of esoteric. This is the least interesting of the 4, in my opinion. It comes up least frequently. But this is the one related to conflicting dependencies. Imagine that we were building this photo share service, and it took a dependency on some shared library, and it used version 1. And in this case, we're building the monolith. So in the monolith, I also want to include the thumbnail code as a library, and it has a dependency on the shared library version 7. Well, we have a problem now. The problem is that I can't put 2 different versions of the same library in the same process at the same time. So we have conflicting dependencies. This guy has linked to version 1, and this guy has linked to version 7. And those conflict. I see somebody's asking a question. All right, but I'm going to answer those during the break. That's fine, though. You can ask the questions now, and I'll get to them later. So this we can't actually make it work. So one thing that we can do to make this work is we can split it up into microservices. So we can run the photo share service with its version 1 as one service, and we can run the thumbnail service with its version 7 on 2 different machines now as 2 different services, and now we can make this happen and everything can work okay. So these are the 4 reasons I can think of to split a microservice up, or a monolith up into microservices. Some other things I'd like to say, I've read a lot about what other people say about microservices. And when I read those things, they frequently talk about some benefits of microservices. And some of the benefits that they talk about, I don't actually think they're benefits. I think they're myths. And so I'd like to point those out. The first myth that I hear people say a lot is that microservices offer small, easy to understand and easy to manage code bases. I mean, yes, that's true, but microservices don't enable this to happen. This was always doable. A monolith can use object-oriented programming techniques and different libraries or DLLs in order to do the same exact thing. In other words, we didn't need microservices in order to make this happen. You've been able to do this for many decades now. And what it really requires is just some developer discipline. So some of the companies I talk to, they say that, well, our software developers, they don't have discipline. And they go and they write whatever they want. And they make this spaghetti code that we can't untangle. And by splitting things up into microservices, we are forcing that discipline on them. Well, that may be true, that you're doing that, but I'm telling you that creating microservices comes with a lot of pain, which is what I'm going to be getting into next, by the way, is all the pain. And so it's a lot less painful if you can somehow force this developer discipline without forcing microservices to happen. And I'm a big fan of library changes causing build failures. When somebody goes and changes the signature of some function in a DLL, and then my executable doesn't link to it anymore correctly, I love that. Because now I know the program is not going to work correctly at runtime, and I can go and fix the problem. But when you do things as microservices, and they're talking to each other over the network, if someone changes the server, and the client is just not directly linking to it, but is just going making network calls, then the client's just going to try to talk to it, and it may or may not work at all. Oh, is there something wrong? Somebody's IMing me now. Is everything going okay? Give me a thumbs up if everything's okay.
Yeah, it's okay now.
Yeah? All right, good. Then I will ignore who's IMing me and I'll continue this on. Go with this. All right, good. The other, what I would say is a myth, is that a failing service doesn't impact other services. Well, many services require dependencies to be fully functioning. So, for example, if my authentication server is down, when a client tries to log in, a lot of times the rest of the service is pretty useless unless that user can be authenticated. So it's hard to keep the code running and doing something useful, even if some dependencies are not functioning. Even if it is possible, a lot of people don't write the test code to test this and to gracefully recover when the dependency fails. And really, in this world of orchestrators that we have now, which I was just talking about on the couple slides ago, we've never run one instance of our service. We always run multiple service instances, so there's no such thing as true failure, right? From the client's perspective, right? A service can go down, a node can go down, but the client will retry and will be sent, and their request will be sent to a different instance of the service. So it never really looks to the client like a service has gone down and has failed. So that means if you run things correctly with an orchestrator, it means that the dependency service is never really gone. It may be running with one less instance, but it's always there functioning in some fashion. And another benefit to monoliths is that they're either up or down completely. They're not half up and half down because some of the code's on this machine and some's on this machine. It's all on this machine. So it's either all up, or if it crashes, it all goes away. which means you don't have to write any recovery code to deal with that. And the infrastructure, or what I mean is the orchestrator, it restarts failed instances, keeping them up all the time. So this is a benefit that a lot of people say by having microservices, that one thing crashes, the rest of it doesn't necessarily crash. I mean, in concept, there's some truth to that, but in reality, it's very hard to do that right, and with orchestrators, it never looks like that's true anyway. So that's why I mark this as a myth, and not as a true benefit. I mostly put this here for reference. I don't want to spend a lot of time on it, but I wanted to briefly mention about service level agreements. You know, a lot of times people say, well, we have a service, and if you offer 99.995% a service level agreement, you are saying that your service can go down at most 132 seconds per month. And if you offer 99.999 or 5 nines of SLA, that means you're not going to be down more than 26 seconds per month. Well, if this service offers this, and service B also offers that, that means that you're now really at 99.990, right? You have to multiply these out, and the more microservices you have that talk to each other, the harder it is to get a higher level of service level agreement. That's what I'm trying to show here. If you have service A talks to service B, talks to service C, talks to service D, then the best you can really do is 99.98%, or 99.96 means you're at 104. It's really hard to maintain a high level of service level agreement when you have a lot of network communication. And furthermore, those are the SLAs of the services, but what about the network SLAs? So what about this network in between here and here and here, right? You probably don't even have SLAs for those, but if you did have SLA numbers for them, that would make this even harder as well. I mean, not knowing it makes it really, really, really hard. Knowing it at least gives you something you can strive for, but usually you don't know what it is. So the point I'm trying to make is, trying to maintain a high SLA gets much harder when you do more network communications and you split things up into microservices. All right, so now, that was kind of my overview, but I have much more to say. Oh, we're at the 9:40 mark though. So should we break here?
Yeah, let's make a break now, and this is time for questions. We have 10 minutes for questions. I think we can start from Slack channel, and then can go to live questions.
So I'm looking at Slack, and Eula team asked a question. Is it okay to share one data store for different microservices? And the answer to that question is no, if you really strictly want to adhere to microservice, tenets, rules, and regulations. If you are accessing a single data store by different services, then you can't really say it's microservices anymore. Because you've lost your data encapsulation, right? It's like making the fields of your class public, and that means that any piece of code can go and change those fields externally. It also means, like, let's say, for example, one service wants to change the schema in that data store. Well, if it changes that schema now, then it would affect the other service as well, right? So now the microservices are not isolated anymore, and that's why it would be a very bad thing to do. Another question from Artem here is, what are the best ways to provide ACID-like behavior in microservices? Well, that's a really hard one. So I'm glad you said ACID-like, because true ACID behavior is really near impossible. I mean, it's practically impossible to do that. So there is a pattern known as the SAGA pattern, S-A-G-A pattern, and it is a pattern that lets you get ACID-like semantics. Basically what the pattern does is you go to one microservice and you say, please do this operation, and then when it's done, you go to the next microservice and you say, please do this operation. So you can go to the order service, for example, first, and say, place the order, then go to the inventory service and say, take the items out of inventory. But that's not true ACID, right? Because those things do happen independently of each other. It's more of an eventual consistency model where you place the order first and you place the removed item from inventory second. And yes, there's race conditions there and concurrency issues there, but it's really the best you can possibly do. If you truly need ACID semantics, then probably all the operations related to that have to be in a single microservice, and you should not split it up across different microservices.
Okay.
Anybody else want to ask some questions?
Thank you. Yes. We have a question from a guy from home.
Thank you. And I have a question. So when we are building microservices and splitting them up, and is it a good idea to create public library, client libraries with microservices, like like public interfaces? When sometimes usually people don't do that, and when some signature method changes, so we have a lot of pain in that way.
Oh, I think I know what you're talking about, and I think I'm going to address that soon in this presentation. So when I start talking about how to do networking between services, I will talk about the contracts between those services at that time, and I will give recommendations for what to do there. So I think I'll be answering your question soon.
Thank you. We have another question here.
Thank you for presentation, and I have a question about is there any cases when you cheaper and when you can cheaper build some infrastructure locally in your data center than use Azure or other services? So is some reasons to build something like Azure or I don't know in your local data centers than use public services?
All right, so let me see if I understand the question. I think you're asking, is there a time when you would prefer to have an on-premises data center as opposed to use a public data center?
Yes.
Is that basically the question?
Yeah, you build some infrastructure locally in your data centers and use public clouds or other services. Is there any reasons to build something like that? Do something like that?
Sure. So I guess the reasons why to build your own data center, I think they're becoming fewer and fewer. I mean, obviously that's what people have done in the past for the last, decade or 2 decades of time, is they built their own data center. The idea is that, having the real estate for a data center, paying for the power, paying for the networking, hardware, all those things dealing with failure, having people in the data center to fix all those failure problems and buying new hardware, refreshing the hardware every couple of years to what's new, refreshing the networking, the cables, the routers that's new periodically. This all becomes incredibly expensive. Refreshing that hardware and hiring the people to do it becomes very expensive. And so the promise of these public clouds is that they're managed by experts. This is all they do, all the time, every single day. And they are buying new hardware, and they're getting economies of scale with that hardware. Microsoft, we buy hard disks in the millions of hard disks, right? Many thousands of hard disks with each order, at least. Right? And so we can get them a lot cheaper than a lot of other people can get them, and we can pass that savings on to you, the customer. And then we have people managing these enormous data centers with lots of machines. So the idea, and this should get cheaper over time as well. So the main reason why I think you would run your own data center today is because it does take some effort to set up all the automation. It takes some effort to design your applications for failure. And so you could throw hardware at the problem today. If it's hard to scale your service up, you can go and buy a bigger machine in your own on-premise data center. And there's other reasons why people don't use public clouds. There could be data sovereignty issues. In Germany, for example, they have a lot of laws that data for Germans have to remain inside that country, and it's not allowed to go somewhere else. So if the cloud provider you're interested in doesn't have a data center in Germany, you might not be able to put data for German customers in there. So there's some geopolitical reasons and data sovereignty reasons that are not technical in nature why you might want to have your own data center on premises. Over time, we let those reasons become fewer and fewer. And laws change and regulations change, compliance issues, things like that do change. Any other questions?
Yes, hello Jeffrey. When talking about splitting into microservices, you said that one of the reasons can be like if different parts scale independently. Can you please explain how this works? Can like the same kind of thing be done via just operating system task scheduling? Say in the holiday season, one VM spends like 80% of time doing thumbnails and 20% of time doing just images, and other times like the ratio can be different. Whereas when we split this, like for every VM, like it has to be allocated entirely for thumbnails or images.
So typically you would have a bunch of VMs for the front end, and you would have a separate set of VMs for the thumbnail images. The front end being the photo share service, and the thumbnailing being the back end service. And sure, you can have an 80-20 split today, across, let's say, 10 nodes, and you can have a 50-50 split tomorrow across those 10 nodes. But with any luck, whoever's building these services is hoping also that over time you get more customers. So instead of 10 nodes, you now need 20 nodes or 30 nodes or maybe 100 nodes because you now have 1 million customers that are pounding on your website, uploading and downloading photos. Right? So the 80-20, the split can vary, of course, but it's really the number of nodes that you need for the front end based on the customer load and the number of nodes you need on the thumbnailing based on the number of videos that are being uploaded. And the resource requirements, right? The thumbnailing, as I said, is a CPU computationally intensive task, so it needs more CPU resources. You might want to have faster CPUs for those nodes, or you might want to have more RAM on those nodes than the RAM you have on the front end nodes, because they basically just get a client request and maybe they just give a link back to someplace where the file can be found. Right? So you might have different resource requirements depending on what your service needs as well. Right? And by splitting it up into microservices, you have a lot of control over this. Right? I can say the front ends, they need these low-powered CPUs on machines with not a lot of RAM. The other ones, they need high-powered CPUs with lots of RAM, and then I can scale them independently, and as my service grows with more customers, I can scale them up, or scale them out, I guess is better, independently of one another too. Right? It just gives you this phenomenal amount of flexibility.
Okay, thank you.
I see another question. Some questions came in on the Slack channel. I can answer those.
We have another last question from Hall, and I think the other question can be answered offline after the talk.
Hello,
Okay.
Hello,
Okay.
thank you for your speech, very interesting. My name is Alexey, I'm from Ingram Microcloud. And my question is, you talk that sharing one data store between several microservices is a bad design. Okay, I agree with you. But what about having one microservice that have access to the data store and all other microservices access to the data store via these microservices? Is it good design or bad design? What's your opinion?
No, that's fine. That's fine. Right? So again, it's just like object-oriented programming. I have a class that has some private fields in it, and I make those fields private. The only way to access that data that's in those fields is for some other piece of code to go and call the methods of it. It's the same thing with a microservice. So I have a microservice, it is its data store, and then it offers methods or operations that go and retrieve data or manipulate, change data in that data store. So then other microservices can go and communicate with the inventory service or with the order service to go and say, what orders has this person placed? And then maybe the order service returns that data back out of its store, and then maybe the front-end service formats that data to look nice so they can either email it to the user, or maybe they can show it to the user in a web page. That's perfectly fine, and that's done all the time.
Okay, thank you, Jeffrey. I think we can proceed now.
All right. I gotta say, I think this is actually working pretty well. I'm rather surprised. But I think this is working good.
Me too, actually, yes.
All right, great. Okay, so I think I'm running a bit behind schedule. So for this next section, I was going to talk about 12-factor apps. And there's a website here where I would recommend you go and read this and learn about it. I'm not going to walk through these 12 factors and explain what they all are to save a little bit of time. But the core concept here is it's all about creating your services to be very, very simple. They should be like console applications, have very few dependencies, start very fast, crash and be restarted by the orchestrator, don't put configuration in code, and so on. And I highly recommend you go to that website and read about these 12 things that's highly recommended when building a service. Okay, so now let's talk about the networking communication, and this is where I'll answer the question that the other person asked on my left side of the room a little bit earlier. So to start with here, there is a document called the 8 Fallacies of Distributed Computing. And I would also highly recommend that all of you find this document and read it. And I give the link to it up here at the top. And down here is the list of fallacies. But basically, what these are all saying is that the network is unreliable. And it's not free. When you make a network request, you may or may not ever get a response back. And it's not, one fallacy is that it's secure, but it's not secure. So you have to secure the data, and so on. And so when you break a monolith into microservices, you're putting a network in between those services. And now that network is subject to these 8 fallacies of distributed computing, all of these things. And you as a software engineer have to write your code to be able to deal with these things. So now, let's talk about what we can do to help us with this. So to keep our services with high availability and scalability, we're going to run multiple instances of a service, right? Our orchestrator is going to run multiple instances of a service on different virtual machines. And we're going to do this because a service may fail at any time, and then the orchestrator should recover. And also, we want to be able to scale our service up and scale it down so that we can handle more load that's coming into our service as our service gets more popular and we have more customers using our service. But we have a problem with this, and the problem is that when we talk to services, as they crash and come back up, and as they scale up and scale down, the endpoints of these services, they dynamically change over the service's lifetime. The IP address isn't always the same. The IP addresses are constantly changing. That, from a developer's perspective, is a nightmare to deal with. I'll tell you, the networking aspect of microservices has caused a phenomenal amount of pain, well, for me personally, I can tell you, and for a lot of customers that I've worked with too. The networking, people think, oh, I'm just making a network call. It is never that simple. Okay, the networking really has significant complication into the system. And here you see some of it. We have multiple instances, and the endpoints keep changing on you dynamically. So ideally, we would like to extract this from our client code. So our clients don't know that applications are crashing and restarting, or that they're being scaled up and scaled down. Each client really wants to have a single stable endpoint as the face of the dynamically changing service instance endpoints. That's what we would like to have. And typically, we accomplish this using what's called a reverse proxy. So this means that every client request is going to go through the reverse proxy. Now, this level of interaction causes an extra network hop, right? So that's going to hurt our service level agreements, and it's going to increase our latency, but we're going to get better fault tolerance right? So the way I look at everything is what are the pros and cons, right? So there's a con here, there's two, right? There's an extra network hop which increases latency, right, hurts our performance, and there's the SLA that's going to be hurt a little bit by doing this as well. So that's the downside. What's the upside? The upside is we get scalability and we get fault tolerance. And so I think they're a good trade-off to make. Right? So we're losing some performance to gain a lot of benefits. Right? The client is going to use some kind of domain name service, a DNS, which is at a well-known static endpoint, to get the reverse proxy stable endpoint, and then the DNS endpoints are usually cached, and they are re-resolved infrequently. And this can improve performance. So here's a slide where I just talked about the reverse proxies on the right-hand side. So basically, client requests end up at the reverse proxy, and the reverse proxy knows how many instances of the servers are here, and it knows what their endpoints are. The clients know the endpoint of the reverse proxy. The clients do not know the endpoints of the servers over here. But the reverse proxy knows the endpoints of the servers. And so that's how we've inserted this level of indirection, which is giving us this abstraction. Now, on the slide, I also put forward proxy, which are frequently just referred to as proxies in general, but sometimes people call them forward proxies. And this is an optional thing to have. And then I give a list of what some of the benefits are. So sometimes people use a forward proxy in order to do content filtering, like censoring certain content, or maybe translating from one language to another language. Everything that comes back into this client infrastructure, the proxy can translate to a different language. Where sometimes forward proxies do caching or logging or monitoring or client anonymization. I just put this up here, even though I'm not really talking about forward proxies, I just did it to introduce the term, because you might run into it at some point in your life, and typically what a forward proxy is used for. But really for our discussion, I want to focus on the reverse proxy, because that's what's important for this part. And a reverse proxy, as I said, it offers a stable client endpoint over the ever-changing server endpoints. It can do additional features too, like SSL termination. It can do caching of data. It can do authentication and validation here, so it doesn't have to be done by the services. It can do load balancing, and there's two kinds of load balancers. There's a level 4 load balancer, which can load balance UDP or TCP traffic, and there's also level 7 load balancers, which balance HTTP traffic. They can also do server selection, or they can be used to do A/B testing. Maybe this is version 1 of some code, and this is version 2 of some code. The reverse proxy can send 80% of the incoming requests to version 1, and 20% of the incoming requests to version 2. So that allows you to do A/B testing of 2 different versions of your code simultaneously, to ease the migration of customers using version 2 of the code. The reverse proxy can be used to do tenant throttling and billing. Like you only allow so many requests per second to come into here. They can also be used to do distributed denial of service mitigation. If you get a lot of clients and they're all pounding on the same service, the reverse proxy can do some analysis of that and say, well, I see there's 1 million requests per second coming into this one service. I'm going to just start dropping packets and not forwarding along. This way your service doesn't have to deal with the denial of service. So my point being is that reverse proxies do this stable endpoint over changing endpoints, and that's really what I'm focusing on, but they can also be used for lots of other things too. They are incredibly useful technologies to have and to insert into your cluster of nodes for doing communication. All right, so now let's put all this together. So here I have my service, and it's very similar to the one I showed earlier, where I have my 3 websites running on 3 different the one website microservice, but it's running on 3 different virtual machines. And then I have the inventory service also running on 3 virtual machines, and I have the order service running on 2 VMs. And I don't show the data stores here because I just didn't have room on the slide, but they would have their data stores like they did before. I've also introduced a DNS server here that has for the inventory service, it knows the reverse proxy that's being used for the inventory service, and it knows the reverse proxy that's being used for the order service over here. So now let's say a client request comes into the data center and it hits the load balancer. By the way, a load balancer is a type of reverse proxy, right? So this is also a reverse proxy, right? It's a load balancer reverse proxy. So this load balancer gets the incoming request, and then it picks one of these 3 virtual machines at random to send the request to, right? Because it's a load balancer, it balances the load across those VMs. So let's say in this case, it sent the request to the website number 1. So now this website number 1, it needs to go to talk to an inventory service, but it doesn't know the address of the reverse proxy for the inventory service. So it makes a request to the DNS service and says, hey DNS service, I'm looking for the inventory service. What is the endpoint for its reverse proxy? And the DNS service returns that back. Now the website service can go and talk to that reverse proxy for the inventory service. And again, this is acting like a load balancer in this case, where it can go and send the traffic to one of these VMs. In this case, it sent it to number 3. And again, as these VMs, they come up, they go down, as it crashes, as it restarts, as we scale up, as we scale down, right? The orchestrator that's being used to manage all of this, it would be updating the reverse proxy automatically for us. And that means that these websites, they don't know how many instances are here. They don't know if they're crashing. They don't know if we're scaling up or scaling down. The only thing they have to do, though, is they have to do retries. Because we could make a request from here to here that comes over here, and as this is processing the request, it could crash. So now this guy doesn't get a response, so he's going to have to retry. When he retries, he'll make a request to the reverse proxy, and the reverse proxy will now send a request to 1 or 2, but not to number 3 because it's down. And now 1 or 2 will do the processing and hopefully send a response back. And then it looks like everything is functioning properly, right? This is how we design things for the scale, and you writing your code to do those retries is a critically important part of making this work. All right, and then I have some notes here. It's impossible to keep the endpoints in sync as service instances come and go. So the client code must be robust against this. That's the retry logic that I keep talking about over and over again. You have to have that there in order to keep things robust. And then I do have another point out here. What happens if website 1 could fail before the inventory number 3 sends a reply? Well, this could fail, right? We're embracing failure because that's designing for the cloud. So this could fail. That means that the user running the browser is not going to get a reply back. Well, most likely the user over here will hit F5 to refresh the page. And that's their way of doing a retry. So they'll hit F5 to refresh the page. That will cause the request to come into the load balancer, and the load balancer, instead of going to website 1, might now send it to website 2, and then the whole thing continues running and everything is back to working again. Right? That's how we design everything to embrace failure and to be able to recover gracefully. Okay, now, turning a monolith into a microservice, when I talk to people about it, they say, well, so this is what my monolith looks like. Inside my application, I call a method, I'll just call it method, and I pass it some arguments. And this method's going to give me a result. So what I want to do is I want to take the code that has method in it, and I'm going to break that into its own microservice. And the code that calls method, I'll keep that into its own microservice. So to break this monolith into a microservice, all I need to do is really just replace this with a network call. Well, that sounds, again, really, really simple. But it's so much harder than people really think it is to do it right. So let's walk through some of the issues. First of all, you now, and this is where I'll start answering that person's question, right? In order for this to work correctly, you need to define an explicit programming language agnostic multi-version API contract. Because now you're talking over a wire now. And so you need to define a wire protocol that is explicit and is programming language agnostic. Remember, one of the benefits of microservices is two different technology stacks. I can use Node over here, and I can use .NET over here, or I can use Java over here, or Ruby over here, right? So what allows them to communicate with each other is the wire protocol. The wire protocol is the contract, and it is programming language agnostic. It should not be tied to a specific programming language. And you have to think about versioning it over time, right? Because you're going to add new APIs, or you might change the behavior of an API. So now you have to start thinking about all of these things when designing this explicit contract. And because you're talking over the network, you're going to lose certain features like IntelliSense, and you're going to lose refactoring, and you're going to lose compile time type safety, right? So you're going to give these things up. Now let's take a look at the arguments. The arguments that you pass here, these now have to be serialized into a byte format to be sent across the wire. Serialization, and then they'll be deserialized on the other side. Serialization and deserialization is not cheap. They are very expensive operations. We have seen some customers where they're complaining about the performance of their program, and when we hook a profiler tool up to their program and we analyze it, we see that a lot of the CPU time and memory consumption is in the serialization and deserialization code. That is not cheap, and it can dominate the performance of your application. Certainly if you're doing something like a calculator service, where I'm going to send you two integers and you're going to add them up and send me the result, the adding of the two integers is trivial. There's like no memory, very, very fast. But the serialization and the deserialization to get that data in and out of the service is going to be very expensive. So you really want to think about that a lot. And of course the results has to be serialized on the server and then deserialized on the client. This also means, in addition to all that overhead, it also means you can only use data types here and here that are serializable. So I can't just use any arbitrary data type now. I have to use data types that allow themselves to be serializable. So I've restricted the set of data types that are possible for being sent across. And now let's compare some other things. Let's compare an in-process method call to a networking request. Well, I've already talked about how a networking request is going to have worse performance than a network call. And it's going to increase network congestion. And network requests are unpredictable in time. You can make a network request and the server may never respond. It might go into an infinite loop and you'll never get a response back. Or it might take you an hour to get a response back. It's far less predictable in time than simply making a method call that's in your own process. The network is unreliable. This goes back to that 8 fallacies of distributed computing, where one of those fallacies is that the network is unreliable. And therefore you have to do retry loops. And when you do retry loops, you probably want to use some kind of backoff, like an exponential backoff. And you probably also want to use something like a circuit breaker pattern as well. I don't have time to go into these here, but these are things that you can go look up to learn more about. And when you have retry loops, the server code must be idempotent. That is, it has to be able to get the same request multiple times and work correctly. Not do, if you say subtract $100 from a bank account, you can't execute that twice because you'll end up subtracting $200 from the bank account. So you'll have to somehow write that code to be idempotent so that it works correctly. And the way that you do that is very domain specific. If I do tell a bank account to subtract $100 twice instead of once, that's a real problem, and I have to write code to deal with that. On the other hand, if I take a picture and I ask the thumbnailer to create a thumbnail of the same picture twice, it's going to produce the same thumbnail image both times. So that's naturally idempotent, but the bank account example is not naturally idempotent, and you have to do something about it. Now, before you stand a microservice up on your network, it's really accessible by anything on the network now. Whereas a DLL that contained this method code is only callable by the process that owns that DLL. So when you put something out as a microservice, you now really have to think about security. And this requires authentication and authorization. And you're sending bytes across the wire. Could something else see what's coming across the wire? So now do you want to add encryption to that so that the bytes are not seen by other services, right? So this is another thing you now need to think about. A lot of times for security, we use things like OAuth tokens, and these tokens expire. So how do we deal with renewing these tokens periodically as we're communicating, right? So it adds a lot of complexity here for the security aspects of it. And then, of course, diagnostics is harder now, too. We now have network issues. That would never happen if you were simply calling method, but now maybe the network went down, or maybe there was congestion on the network, and that's what slowed down the call. And when you want to look at things like performance counters, or events, or logging, then now some of the stack trace is on one machine within one microservice, and some of the stack trace is on another machine in a different microservice. So you might have to aggregate all those stack traces to get a holistic view of everything that happened and how you got there. So that's what I'm talking about with causality and call stacks here. It can become much more challenging to diagnose issues that are happening when you have a lot of microservices running around. So I paint a very negative picture with all of this. But why are we doing it then? The reason why we're doing it is for one of these things, right? So the networking, I'm telling you from my experience, it's been very painful. But I'm still willing to do it because I might want to get scale independently, or I might really want to use two different technology stacks, or I might really want to build this service once and version it at will and let multiple clients can use it so that I have reusability of code. Or I might really want to do it because I need to fix this conflicting dependencies. Right? Again, I'm a software engineer. And so whenever I look at a problem, I look at what are the pros of this particular solution and what are the cons. There's a lot of cons of introducing networking. So am I willing to do it? Yes, if I want one of these pros bad enough to do it. And those are certainly real life scenarios where people want these things. So then I'll go through the pain of doing the networking. If I don't want one of these four things, then I won't go through the pain of adding in the additional networking. And now I have a little bit more to say about contracts, again, addressing that person's question that they asked during the break. So define an explicit formal cross-language API and data contracts. Contracts defined via code do not work. If you've been in the Microsoft space for a while, especially if you use Windows Communication Foundation, WCF, Microsoft used to promote this code first or contract first methodologies, where they could say, well, you could write your contract by doing it in XML, that was what they used in that day, or you could write your contract in code and then use the code with tooling to produce the XML. My experience has been that producing contracts with code does not work. The tools have special knowledge about certain things. There are things that are implied that will not be taken into consideration. So I have some example. Well, I have one example here on the slide. There are a lot of people in .NET that write a contract like with a C# interface where the method takes a date time. Well, if the client who's trying to pass you this in your contract, if the client is a Java contract, in Java, a date time can be null. But in .NET, a date time cannot be null. And so you in your C# code in your service would never expect the client to pass null. But if the client's a Java client, they can pass null. How about in .NET, we have nullable types, right? A nullable value type. Well, in Java or in other languages, they don't have a nullable value type. In .NET, we have generics, but in other languages, we don't have generics. So if you use these language constructs to create your contract, then it's not guaranteed to work in other languages. And so it just doesn't work, and it's too easy for it to fall apart. So my recommendation to you is do not produce contracts using code. It is very unlikely to work for you. So instead, produce your contracts. I mean, typically today people create HTML-based contracts. So use a tool like OpenAPI or Swagger tooling, and create your contracts that way as pure HTML contracts. If you want to use like Google RPC, that's a fine way to go too. Or if you want to use TCP, you can, but define what the byte protocol is that goes across the wire. That's a real contract. And make sure that that contract will work for multiple languages. So I give examples here. Use things like JSON and XML, because those are cross-language, right? There's other serialization technologies like Avro, Google's protocol buffers, Slack buffers, Thrift, Microsoft's Bond. These are all examples of technologies that can serialize and deserialize, and they're all designed to work with multiple languages. Consider embedding a version number in the data structure. And then, optionally, you can work with JSON and XML on the client and the server. But a lot of times, software developers, we don't like working with XML and JSON, right? It's a lot of string manipulations, and we don't get type safety, we don't get IntelliSense, we don't get refactoring support. So you can also, after you create the contract, you can create a client library. And the client library, you can create one for .NET, and you can create one for Java, and you can create one for Python, and so on, for each language. But they're built on top of the contracts, and that will allow the client and the server to be written in different languages and be able to communicate with each other. Realize, of course, that those client libraries, they do serialization and deserialization, and that can be a performance hit, right? It can use RAM, and it can CPU costs with this. So just be careful of it. It's useful. A lot of the programmers love it. It simplifies your programming life. It does hurt performance to do that, and you have to be willing to make that trade-off. This is another one that's related. Beware of leaky RPC-like abstractions. Programmers love RPC mechanisms because it makes the network call look like a method call. And there are a lot of technologies that try to map these method calls to network calls. Examples of these technologies are things like RPC, RMI, Corba, DCOM, WCF, etc. A lot of times these technologies also don't work well. They have problems with them. A lot of times those problems exist due to the 8 fallacies of networking, distributed applications that I talked about earlier. So they don't do things like retry loops. They don't take advantage of circuit breaker patterns. The retries may not use, if they have it at all, they may not use an exponential backoff pattern. They may use some kind of linear backoff pattern or something that you don't want. They have language-specific data type conversions, examples like date time I gave before, or durations. There's no standard for how those things get passed around. How do you deal with different versionings of APIs where the server versions, but the client library hasn't versioned properly, right? Or is calling v1 on the server, but you'd like to call v2 on the server. How do you deal with that? If the mechanism is using some kinds of tokens, authentication tokens, to send from the client to the server, those tokens may expire, so then they need to be renewed. Is that built into this mechanism to automatically renew those tokens? How do you deal with that? And what about logging? If you're making HTTP requests, then you can log what's in the parameters, or what's in the headers, or what's in the payload, or what's in the reply headers, or the reply payload. If you're using these kinds of technologies, you don't necessarily know what's being sent where. Is this a parameter, or is it being sent in a header, or maybe it's being sent in the payload? What's being logged? How is it being logged? How can I track what goes wrong when something goes wrong? So my experience has been, I've used a lot of these in my lifetime, and a lot of times they get in my way. They cause me to not be able to diagnose the problem. They cause me not be able to fix the expiring authentication token. They cause language problems when I go from one language on the client to a different programming language on the server. And so I have been burned by them quite a bit. Again, if you go to that explicit contract, and then use tools to create client libraries from the explicit contract, this stuff gets a lot better. And then you want it to be very lightweight. These abstractions can frequently get in the way, so just be careful of that. All right, so now that was a lot about networking, but there is another kind of communication that can be done between services And that is using messages instead with a queue in the middle. 10 minutes, I see it. Thank you. Which means I'm definitely going to run out of time. But this is a very useful thing, so I'll try to go through it fast. And I put a website here that you might be able to look at for more information, which is the reactivemanifesto.org. I have signed this myself, and I strongly believe in it. So in the interest of time, I'm going to move quickly, but the idea here is instead of having one service talk directly to another service, use a queue in the middle. So this is that website service I showed before, and imagine that this is the inventory and maybe this is the orders over here. But now we're going to insert queues in the middle. So this is a queue for service A, and there's 3 instances of service A. This is a queue for all the instances of service B. And then we have separate queues for website 1, website 2, and website 3. So there's 5 queues now. 1, 2, 3, 4, 5. Yeah, 5 queues that I put into this service. So the client makes a request to the load balancer. The load balancer picks one of the website instances to send the traffic to, in this case, website number 1. Now, website number 1, it wants to go and talk to service A. But instead of talking to the DNS server and instead of talking to a reverse proxy, it goes and puts a message into a queue for service A. And then it can return, right? So it just posts the message in the queue and then it comes back. Now, service A, there's 3 instances, and any one of these instances can go to the queue to pull the message out and return back. There's a big difference here. Okay, when you use a load balancer, the load balancer or the reverse proxy, right? The load balancer or the reverse proxy, it picks one of these at random and sends the traffic to it. But what if website number 1 is 100% of CPU usage? It's very, very busy. And the other 2 might not be busy at all. Well, the load balancer doesn't know that. So the load balancer just picks one at random and sends the traffic onto it. So we may not really be balancing the load equally across these instances. But when you use a queue, it's very different. This service picked up the message from the queue because it was ready to process another message. Right? So this is pulling from the queue rather than the message being pushed into the service. And that's a huge difference because this will pull it at a time when it's ready to do more processing, meaning it's under load and it's ready to take on more load. All right, so now service A number 3, it might need to go and talk to service B. So it goes and puts a message in B's queue and then it returns immediately. And then one of these instances, when it's ready to do more processing, it'll go up to the queue, pull the message out, and now do the processing. Right, so again, it's pulling the message from the queue, so it's a much better load balancing mechanism. Then, when service instance 1 here is done, it can go and post the response into queue A, and now a different service A can pull that message out. So when you do request reply, the response has to go back to the requester. But when you use queues, the response can go into the queue and a different instance can pull it out of the queue. That makes you more resilient to a service crashing. Right? This one could crash, but a different one could go and pick up the reply. And so you're more fault tolerant. And it also makes you more resilient to scale up and scale down scenarios. So I love queues because they fix a lot of problems that direct endpoint-to-endpoint messaging introduces. Okay, and now this instance A can pick up the reply from service B, can do some processing, and now it's going to put something in the queue for web server 1 because this was not done as a queue on the left side here. So we have to get the response from this into website number 1. So this can go and pull the response out of the queue so that it can ultimately reply back to the customer. Right? So this is also showing how we're using queues on the inside, but we're using a reverse proxy or load balancer on the outside. And when you have this here, we needed 1 queue for each of these services. Well, over here, we needed 1 queue for all of service A and 1 queue for all of service B. All right, then I have some notes, but in the interest of time, I'm going to skip those. So the point of that being, using queues is awesome and highly, highly, highly recommended as a much better way of doing inter-service communication. The load balancing ends up being better, and the fault tolerance ends up being better, and actually you can scale things better because you're not using a request-reply pattern. You can post directly to something if you want to. So a lot of goodness for queues. All right, the last topic to talk about is storing state and state management. Unfortunately, this is a big topic, and I'm going to run out of time. So let me say as much as I can in the time remaining. Building a service that manages state is substantially harder than building a stateless service. Like many orders of magnitude harder than building a stateless service. And the reason is because you have to deal with all kinds of additional things, such as the size of the data. Where are you going to store that data? How are you going, what's the speed of accessing that data? If the data is large, I now have to partition the data. I'll put some of the data on this machine, and some of the data on this other machine, and some of the data on this third machine. And then you have to know where that data is to be able to go find it later. Because failure is always possible, you have to replicate the data. So if you put all the data on one machine, and then the hard disk fails, you've lost all the data. So you need to have multiple replicas so that one machine can crash and you lose the data there, but you can go to other replicas to get the data. Well, because you have replication, you have consistency issues. Let's say that I'm changing a value from 5 to 7 on one replica, then it's going to take me time to go to another replica and change it from 5 to 7. Well, what if I can't reach that other replica because the network went out? And then what if there's multiple replicas and I'm able to change half of them but not all of them? Then did I change that value to a 7 everywhere? Or is it a 5 in some places and a 7 in other places? How do I reconcile that inconsistency of the data? How do I deal with disaster recovery? Let's say that I have all this information for customers in a data center somewhere in the world and that data center goes out. Well, I would like to be able to continue serving the customers, so I need a disaster recovery policy set up where maybe I replicate the data to another data center so I can go to this other data center in another part of the world and get that data back out of there. So how do you do that, which is really making another replica, and how do you manage the consistency of that, and what's the latency of storing this data in all these replicas? What about a backup and restore story? Because I might have a bug in my code that corrupts data, or maybe there's a hacker out there who attacks my data store somehow. They get access to it, and they attack it, and they corrupt the data. Well, then I might want to go and be backing it up periodically so I can restore my data to a non-corrupted state. But when I do that, I've probably lost some newer data that has changed. So what are my policies around that? What is my management? It's really a lot about business decisions. So not just technical decisions here, there's business decisions here. How much data is my business willing to lose? If I go to a restore from a backup that was made a week ago, am I willing to lose all the changes that have happened in the last week or not in order to get back to a consistent state? How frequently do I want to do backups? Maybe I'll do backups once an hour because of that. But then where do I store those backups? That's has to be stored somewhere. And how do I secure access to those? Right? There's a lot of issues that come up when you're dealing with state management. Well, that brings us to the cost. It brings us to the administration part of this. Who has access to the data? How frequently do you do it? The security aspects of it. Do we encrypt the data at rest? I don't have that up there, but that's another one too. And encryption hurts the performance of accessing the data. If you encrypt the data on the server, it's hard to do indexes of that data. Therefore, it's hard to do filters and querying of the data on the server. Right? I mean, there's a million issues that you don't have to think about when you're building stateless services that you do have to think about when building stateful services. So because of this, most developers do not build their own stateful services, and I would strongly recommend you don't even attempt it. Instead, use a robust and hardened database service that somebody else has created and tested, and lots of people are using it, and then you feel that you can really trust. something like SQL Server or Cassandra or Hadoop or something like that. Use those kinds of services. Do not try to build your own. It's way too hard. When selecting a stateful service, you must fully understand your service's requirements and understand the trade-offs when comparing available services. There's many different database technologies out there, in the hundreds, and they each do different trade-offs. Some will trade consistency to give you better performance. Some will give you worse performance in order to give you better consistency. Some will use optimistic concurrency, some will use pessimistic concurrency. Some will do lots of replicas, some will do a small number of replicas, some are configurable. You really need to think about all of this and understand it before or when you're deciding which database technology to select for implementing your microservice. And it is common to use multiple stateful services within a single solution. So for one microservice, I might use SQL. For another microservice, I might use a different database entirely because it's different needs for the other microservice. The end point, or the takeaway from all this is, the stateful part is really, really hard. And there's many issues to consider, and you really need to think it through and analyze it carefully. All right, at this, I think I'm over my time. But I have many more slides. You can download the slides and get to it. And someday I'll record all of this. And then you'll be able to watch that video. Are there any final questions or anything before we sign off?
If you can do it, we have time for a couple of questions. Well, question here.
Thank you for the speech. I have a question about message queue. For example, we have order service and we have record service, and both of them have their own database. And order service sends some messages with orders metadata. Record service handles them and aggregates them and stores them in their own database. And how can we handle such some kind of errors in that case, like message was lost or record service handled it wrong, and in the result our data become unsynchronized?
Okay, so I'm having a little trouble hearing, but I think the question was, if you use messaging to communicate, and then the service gets the message, starts processing it, and then crashes, then how do we make sure that the message really gets processed?
Yes.
Is that the effect? Like, how do we do retries with a queue?
Yep.
That's the question? I took that slide out of the deck because I figured it would take me too long to explain it, but I'll give you the short version. So you need to use a durable queue service, and that would work something like this. So a client puts a message into the queue, the server pulls the message out of the queue. The server is now processing the message, but the server crashes while processing the message. So when you pull the message from the queue does not delete the message. Instead, the queue hides the message. It's usually called a visibility timeout. It makes the message invisible, but it remains in the queue. So any other machines, services that are trying to pull that message, they won't see it because it's invisible. But the invisibility has a timeout on it, let's say 1 minute. So if after a minute, the server that got that message doesn't go back to say, now delete the message because that service crashed, the message will become visible again. So now some other service will come to the queue and say, I need a message, and the message will be delivered a second time. And now this other instance will be processing that message, and the message will become invisible again. And if it crashes, then it becomes visible again, and you process it again. But if we process it successfully, then the service that processes it goes back to the queue and says delete the message. Now this means that the message can be delivered more than once, which means that the processing of the message has to be idempotent, just like in the retry case. Right? But that's how we solve the failure problem, where we're processing a message and it fails. And by the way, the queue maintains state, right? It has the state of all the messages. So the queue technology that you use must also replicate the messages, and everything I talked about on this slide about partitioning, replication, consistency, all of that applies to the queue messages too, because those are pieces of state that need to survive failure. But the queue can't fail. The queue has to keep the data alive. So you want to use a queue service. You don't want to build the queue yourself, because in effect the queue is a database, just like a database, like SQL would be a database.
Okay, many thanks, Jeffrey. We are out of time now. Let's clap in for Jeffrey and many thanks.
Thank you.